Welcome to The Explainer. Today we're going to dive into a world that is, well, it's just plain weird. A world where particles can literally be in two places at once, and where a choice you make right now can apparently change something that already happened. Yep, this is quantum mechanics, and it's about to completely mess with your idea of reality. So let's get into it.
Right off the bat, we have to just throw our basic assumptions out the window, because what we're about to see is that at the tiniest, most fundamental levels of the universe, the rules that we think govern everything, they just don't apply. It's a whole different ballgame. But, okay, before we jump into all that weirdness, let's set a baseline. Let's talk about the world we think we live in, the world of classical physics. You know, the intuitive, predictable world of Isaac Newton, the one that just makes sense.
And this really gets to the heart of it. See, in the classical view, everything's like a giant game of pool. If you know exactly how you hit the cue ball, the angle, the speed, you can predict exactly where every other ball will end up. It's determined. But the quantum view, it throws all that certainty right out. It's a universe of probabilities, a world of maybes instead of definite yeses.
So, what was the first big hint that something was, well, deeply wrong with our nice, tidy, classical picture? It actually came from an experiment that's shockingly simple, but its results, oh man, they open up the biggest mystery in all of physics.
And I'm not just being dramatic here. The great physicist Richard Feynman himself said that this puzzle is the absolute core of quantum mechanics. It's a mystery that you can't explain away. It refuses to go away.
Okay, so here's the experiment that started it all. Imagine you have a barrier with two little slits in it, and you're going to fire tiny particles of light, photons, at it, one at a time. Behind the barrier, there's a screen to see where they land. Simple enough, right? What would you expect to see?
Logically, if photons are like tiny little bullets, they should just go through one slit or the other and make two distinct lines on the screen behind them. But that is not what happens. Not even close. Instead, you get this weird pattern of many bright and dark stripes. And that pattern, that's an interference pattern. It's the unmistakable signature of a wave passing through both slits at the same time and interfering with itself. And that right there is the fundamental mind-breaking question. How? We're sending them one by one. How can a single photon go through two different places at once? This bizarre, impossible-sounding behavior is what we call wave-particle duality. And it's the first sign we're not in Kansas anymore.
Okay, so naturally, physicists saw this and said, all right, let's just peek. Let's put a tiny detector by the slits and just watch to see which one the photon actually goes through. And the moment they did that, well, the universe decided to get even stranger.
Now, to understand what happens, you gotta know this one key rule of the quantum world, the Heisenberg uncertainty principle. It basically says there's a fundamental limit to what you can know. The more precisely you measure a particle's position, the less you know about its momentum, and vice versa. It's not about bad equipment. It's a built-in feature of reality itself. The universe has a fuzziness slider, and you can't turn it all the way down.
And that's exactly what happens in the experiment. The second you place a detector there to get that witch slit information, poof, the wave pattern completely disappears. The photons suddenly start behaving like normal little particles again, making just two simple lines on the screen. The very act of looking, of measuring, forces reality to make a choice.
But it gets crazier. The physicist John Wheeler came up with this brilliant, mind-bending thought experiment. He asked, okay, what if we wait? What if we decide whether or not to measure the path only after the photon has already gone past the slits? And unbelievably, they've done this experiment now, and the results are just staggering. It turns out that even if you make the choice to measure after the photon should have already passed the slits, the outcome changes. It's as if your choice in the present is reaching back in time and affecting the photon's past behavior. It seems to break our whole concept of cause and effect. So, if a future choice can affect the past, what about connections that can defy huge distances instantly? Well, this is where quantum mechanics gets, in the words of one famous scientist, truly spooky.
You know, it's funny. Albert Einstein, one of the godfathers of quantum theory, ended up being its biggest doubter. He absolutely could not stand one of its core predictions, something called quantum entanglement. This is the idea that you can link two particles so that they share the same fate. You measure one, and you instantly know the state of the other, even if it's on the other side of the galaxy. Now, to fight against this, Einstein held on to two ideas that
let's be honest, just feel like common sense. The first is realism, that a particle has real, definite properties, like spin, even when we're not looking. A ball is still red in a dark room, right? The second is locality, that nothing can travel faster than light. No spooky, instantaneous action. Make sense? But here's the knockout punch. For decades, physicists have run incredibly precise experiments to test Einstein's local realism against the spooky predictions of quantum mechanics. And the verdict is in: Einstein was wrong. Our common sense view of the universe is just wrong. Reality is either not local, meaning these spooky connections are real, or it's not real, meaning properties don't exist until we measure them, or maybe even both.
So, where does that leave us? Reality isn't what it seems. It's not local, it's not quite real in the way we think. It's just bizarre. And this has led to nearly a century of arguments among the smartest people on the planet about what it all actually means. Yeah, what does it all mean? Faced with all this evidence that just shatters our intuition, scientists came up with different interpretations. And it's important to know these aren't different theories. They all make the same predictions. They're more like different stories we tell ourselves to try and make sense of the weirdness.
So you've basically got two major camps. The standard view, called the Copenhagen interpretation, says that reality is just a fuzzy cloud of probabilities. Nothing is real until we look at it. The act of measurement forces the universe to pick one outcome from all the possibilities. But then you have views like Bohmian mechanics, which say, no, the particles are real. They have real positions all along. We just can't see them because they're being guided by a hidden pilot wave.
And don't think this is just some philosophical hand-waving. David Bohm built a complete, rigorous mathematical theory. It perfectly reproduces every single prediction of standard quantum mechanics, but the story it tells is of a very different universe, one that is actually deterministic and concrete, just with these invisible, spooky connections guiding everything behind the scenes.
So that's the big question we're left with, isn't it? Is the universe a giant cosmic lottery, where reality only snaps into existence when we observe it? Or is there a deeper, hidden, clockwork reality that we just don't have access to? The debate still rages today. What do you think is really going on?